In the last lesson, we introduced the ideas of electric potential energy and electric potential. And one of the examples I gave was like this. If you were sitting on a water slide, like this, you can measure the amount of energy something would have if you put it on the slide at different heights by measuring the amount of potential at each of these different spots. Okay, and so at the very top of the slide, up here, this position has a certain amount of gravitational potential, and it has more gravitational potential up here than it has way down here. This is the bottom. It has no gravitational potential over here. Okay, and then as you go up the slide, the amount of gravitational potential is increasing until you reach the maximum amount of gravitational potential. Now that's talking about the slide itself. The locations on the slide have potential, but when you put a person on this slide, now this person has gravitational potential energy. By putting an object or person or what have you at some position of potential, you are giving that object potential energy. It works the same way with electricity. So with electricity, let's consider a set of charged plates. So here's our charged plates. Let's say this one is positive, this one is negative. Okay, and so a charge that you place between those plates will want to move until it reaches its position of rest. So let's consider a negative charge. If you put a negative charge in between these plates, it wants to move along the field to its place of lowest potential energy, okay, or to the location with lowest potential. So this negative charge, it's going to be repelled from the negative side and attracted to the positive side, and so this position right over here is the position of lowest potential, and that charge will have the lowest potential energy at that point. Okay, and so up here we have high potential, over here we have low potential. Okay, so that's potential is about the position, it's about the location. Potential energy is about the object. In this case, it's about the charge. Now, we're going to delve a little bit more deeply into all of the relationships that we can see here. So we're going to start out with work. So right now, we're just going to detail a whole bunch of relationships that have come about because of all of these relationships that we've been looking at leading up to now. So, specifically talking about electricity, work is equal to electric potential energy. Okay, assuming that we're starting at a position of no potential energy, so over here, if you would move this negative charge this way, you would be giving it electric potential energy. Okay, and so the amount of work that you do, the amount of energy that you add, is equal to the amount of electric potential energy this charge will have at whatever location you leave it at. Okay, so we can say that work done is equal to the electric potential energy of a charge at some location. We also know that electric potential energy is charge times potential difference. Okay, so the potential difference is the difference in potential from this position to this position, or any position, and the amount of charge that you have is also going to play a role in how much energy it has. A larger charge, or something with more charge, will have more energy over here than a charge that has less charge. Okay, the potential hasn't changed. The voltage change is still the same. It's just that the amount of charge will determine how much electric potential energy it has. We also know that potential difference has its own formula. This is also equal to field strength times displacement. Okay, so the strength of this field is going to determine how much voltage there is. It's going to determine the potential difference. You might also say that that up here, the height of this slide, or the steepness of the slide, determines how much potential difference, how much gravitational potential difference there is between the top and the bottom. So we have now Q times field strength times displacement. Okay, so we're just adding some pieces, some variables into this relationship that we're putting together. Okay, so electric potential energy is going to depend on charge and voltage or potential difference. That also depends on the strength of the electric field we're talking about and how much movement there is, how much distance we've moved inside that field. Okay, we also know that QE is equal to electric force. So then we get force times displacement. Okay, but we actually already knew that force times displacement is work. When we introduced work, that was the definition formula for it. Force times displacement. So we know that change in energy must also be equal to force times displacement. It's just that in this case, it's electric force. Okay. This is also equal to change in kinetic energy and change in potential energy, or gravitational potential energy, depending on what the situation is. So now we've got this whole set of interconnected mathematical relationships, and which relationships you use in any given circumstance depends on what are you looking for exactly and what information have you been given. So you're never going to use this entire thing all at once. That's craziness. You are going to use two pieces at once. So a lot of the problem solving that you're going to see in the homework book is going to have to do with choosing what's the relationship that we're talking about here. Which two pieces do I need to use for this? Before we move on to an example or two, I want to point out one more thing about voltage or potential difference. Let's say we have two charged plates. There's the top one, here's the bottom one. We're going to call the top one the positive and the bottom the negative, but for our purposes this doesn't really matter at all. And our electric field then is going to point from positive to negative. There's our electric field. So when we're talking about voltage or potential, we're talking about a location between these two plates, right? If we're talking about a negative charge, it has greatest potential over here because it has the greatest distance to move. If we're talking about a positive charge, then its area of greatest potential would be over here because it really wants to move to this negative plate. This would be its position of rest. Okay, so let's draw another line right over here, parallel to both plates. Okay, this line would be called an equipotential line. That means that any position on this line is going to have the same potential. It doesn't matter that you're moving laterally. This position over here has the same potential as this position over here. If you move a charge from here to here, it doesn't actually take any work. You're not moving it with or against the field. You are just moving it to another place in the field that has exactly the same potential. Okay, so a charge that you place over here has the same energy as a charge that you place over here. Okay, so this would be called an equipotential line. We can call this voltage A. Now let's draw a second line here, right there. Now the same thing is happening here. Moving a charge from here to here does not change its electric potential energy at all. It just changes its lateral location. So each position on this line also has the same voltage. So we can call this voltage B. It's not the same voltage as this one, because if you move a charge from here to here, you are changing its energy. But moving a charge from here to here does not change its energy. So these two lines, they have different voltages, but along each individual line, each voltage is going to be the same. So each of those lines is called an equipotential line, but they are not the same as each other. Now let's do our example. A Millikan apparatus is in a vacuum and an aluminum ion, which has a charge of +3, is between the plates. The electric field between the plates is 145,000 volts per meter down. Volts per meter. That's usually not how we measure the electric field, or not how we have in the past at least, but let's do a little unit analysis of volts per meter, and we'll see that it's actually not different than what we've done before. So, volts per meter. Volts per meter. Volts is joules per coulomb. Joules per coulomb. If you remember, it's electric potential energy divided by charge. Electric potential energy divided by charge. So that would be joules divided by coulombs per meter. This is actually the same as joules per coulomb times meters. Okay, now joules, remember that's energy or work. That's force times displacement. So force times displacement would be newtons times meters. And on the bottom we have coulombs times meters. So we can cancel out these meters because we have one on the top and the bottom, and we end up with newtons per coulomb. And in the past, that is what we have measured our electric field strength in, newtons per coulomb. And so volts per meter and newtons per coulomb are the same thing. So we're looking for what work is done to move the ion this far from its original position, 1.5 times 10 to the negative 3 meters. So here's our situation, top plate, bottom plate. The field is pointing down. Okay, and that means that the top plate is positive, the bottom plate is negative. We don't necessarily need to know that to solve this question, but sometimes it's helpful for your imagination. Okay, what we're asked for is work. How much work is done to move that distance? The charge on this thing, it's an aluminum ion with a charge of +3. That's +3 ECs, or elementary charges. So +3 ECs. Our electric field is 145,000 volts per meter, newtons per coulomb. Displacement is 1.5 times 10 to the negative 3 meters. So we are trying to solve for work. We're given Q, E, and displacement. So one of the skills that we've been working on in physics is figuring out what is the relationship between all of these different things that we're given. So we look at what are all of the quantities that we know, what's the thing that we're looking for, and what's the relationship between them. So for this one, we're going to look back up at that long list of relationships that we had from earlier. Here they are. Work equals electric potential energy, which is equal to Q times potential difference, which is equal to Q times E times D. Okay, now I see right away that we have Q, E, and D. Those are variables that were given, and we're asked to calculate work. So this is a fairly simple one. I'm given 3 of the pieces, which are all together like this, and I'm just asked to find this other piece. The challenge to these types of problems is figuring out which is the relationship that I'm going to use, because sometimes it isn't as straightforward as that. But now that we know what relationship we're going to use, we can just put it together and solve for the missing piece. Work is equal to Q times field strength times displacement. So the charge is 3 ECs, but the field strength is measured in newtons per coulomb, or volts per meter. And so this version of the charge, we are not going to be able to use that just as it is. We'll need to do a conversion. So in my case, I'm going to go 3 ECs, but I'm going to put that conversion right within this formula. So each EC is 1.6 times 10 to the negative 19 coulombs. 10 to the negative 19. Okay, so now my 3 ECs will be converted to coulombs. Multiply that by the field strength, which is 145,000 volts per meter, joules per coulomb, newtons per coulomb, I mean, times the displacement, which is 1.5 times 10 to the negative 3 meters. That's already in meters, so no conversion necessary. And when I multiply all that out, my work is 1.04 times 10 to the negative 16 joules. Okay, so that's how much work is done. That's how much energy is required to move that charge from one position to another exactly that far. So in that distance, we're looking for what is the potential difference it experiences. The question is asking us for what is change in V. Okay, now we're going to look at our set of relationships again. Where can we find change in V in this list? It's really only in this one place, Q change in V. So we can solve this piece of the problem a number of different ways. If we wanted to, we can go work equals Q times change in V, and then solve for change in V now that we've calculated work and we know the charge. Or we can go Q times change in V is equal to Q times E times D, in which case the Q cancels out, and V is just equal to E times change in D. So there's going to be a number of ways often to get at the information you're looking for, if you know what to look for. I'm going to use V equals E times change in D. Voltage, or potential difference, is equal to field strength times displacement. Okay, that's the relationship I'm going to use. Potential difference equals 145,000 volts per meter times the displacement is 1.5 times 10 to the negative 3 meters. And when I multiply those two things together, I get 218 volts. That's the potential difference that this charge has moved through. That's the difference between the starting point and the ending point. And if we look at the units, we started with volts per meter was the measurement of the field strength, and meters was the distance that was moved, and when you multiply those two you get volts. So often looking at the units is also a good way of figuring out what should I do with these numbers.